Hi, everybody, and welcome to this Neo4j webinar on network and IT operations. My name is Alessandro Svensson, and I work with solutions at Neo Technology. And together with me today, as Corey mentioned, I will have Will Lyon from our developer relations team, and he's going to provide us with some Neo4j and Cypher demonstrations. So thank you for joining us. This is today's agenda. I'm going to start off with a brief intro to the property graph model, and then we'll move on to talk about networks, and in particular what we call the network graphs and the security graphs before we wrap things up. Okay, so let's begin with talking a little bit about the property graph model. Some of you are probably familiar with this, but it doesn't hurt to get into the world of graph thinking a little bit before we start. And I think to understand what graphs are and what they and where they come from, we have to consider the way databases have evolved in order to handle large networks of connected data. And while the traditional databases are great for storing data that is heavily structured, that's just not how data looks anymore. What we see is a huge explosion of connectivity and value being created within huge networks of connected data. And another way to put this is to say that data structures as tables, columns, and rows is evolving to be stored and modeled in a way that the data is relating to itself. And this is what modeling data as a graph is. So a graph is essentially connected data, which essentially means data points, or nodes as we call it, that have relationships with other data points. And this could be a person that has a checking account with a bank. It could be a hotel that has rooms that have availability. Or it could be a social graph, which is people who know other people, who then know other people who perhaps studied together, who work at the same place, or who studied with other people, or who work somewhere else, etc. And this is exactly how data appears in Neo4j. And one of the benefits with this model is that it's extremely intuitive to understand and very easy to model. And the interesting thing is what happens when you start to add more and more relationships to these graphs, and these things start to take off at scale. And then forming an extremely powerful foundation from which you can derive value through analysis, to perform real-time queries, to build extremely powerful applications and algorithms, right? So that was just like a brief intro to get into kind of the world of graph. But today we're going to talk about network and IT operations. And while there are many possible examples of how graphs can be helpful in this space, we're going to focus on two particular topics. First, the network graphs, as we call it, and the security graphs, which are two very important topics in this space. So let's begin with the network graph. First of all, the interesting thing with networks is that networks are basically naturally graphs. And what does that mean? Well, when we say that networks are graphs, we mean that networks by default are entities that are connected, right? So if you do a quick search on network topology, for example, you basically end up with a display of a bunch of graphs. And if we zoom in on one of them, which seems to be a mesh network of some sort with routers and gateways, etc., this would be very easy to translate the model into a graph in Neo4j. So what are the challenges that managers in a network operations center would face on a daily basis? Well, the purpose of an NOC is to, of course, manage, control, and monitor for network reliability and performance. And this requires an ability to monitor the health of an entire network, to visualize and understand how different components correlate in order to troubleshoot, to perform impact analysis, and to plan and model outage scenarios, for example. And the key challenges here is that normally you would use a bunch of fragmented monitoring tools, which gives you an inability to correlate problems in different network domains. And this leads to a series of inefficiencies and often high support costs and penalties. So what are some of the different workloads within network management? Well, they can either be operational, such as real-time event correlations or real-time network analysis for example, single point of failure detection, or have a more analytical nature where you would perform what-if analysis for change management or monitoring for some strategic transitions of technology, for example. So let's look at an example of what a cross-domain network and services topology will look like. First of all, the goal with this is to have, like in an ideal world, you want a single coherent real-time view of customers, services, and the physical networks they depend on. The problem is that often, though, it's not the case. Conceptually, this is how a network normally looks. You will have different domains in different layers, and the ability to map all of this into a unified view is actually very challenging and extremely complicated. So let's look at an example. Okay, so here we have an event that is being reported to a network operation center, and apparently we see here that it's a loss of connection with an interface AX2431. And in this scenario, you quickly want to find out about the impact of this loss of connection. So here we see that we have an enriched event that will help you prioritize the action that you have to take. And here we see that we seem to have a problem affecting a priority 1 customer. So what you need here is an accurate dependency model. And let's see how that would look like when we would model it as a graph. So as you can see, the dependencies of the networks appears very intuitively. And the emphasis here is that your action will only be as good as your model is. It has to be a real-time view of your topology in order for you to take appropriate measures. And in this example of a priority 1 customer, that needs to be fixed right away, which needs to be reported back to you basically as you sit, which means that the systems, you can't base this on systems that require pre-computing. It's just not an option. So apart from having the visibility of a network topology that is provided to you by the graphs, you also need the real-time capability. And this is really only possible with the use of graph databases. Another way to look at this is from an architecture point of view. So here we have a cluster of cross-domain topology service with Neo4j that ingests data from your different existing sources. And in this example, a registered raw event that we saw from before is sent back as an enriched event either to your fault management system or is logged into your event store. But this is the basic architecture for how this will work. And of course, based on the same architecture, we can perform, there's of course other types of uses. We talked about the change manager before, and your change manager will be able to perform what-if analysis and combine those with topology analysis for all the other planned changes within networks, which happens all the time. And all this is made so much easier and accurate when modeling your network topology and storing it as graphs in a graph database. So why would let's talk about what the reason is for why so many companies choose to use Neo4j in network operations. Well, first of all, because of the native graph storage, which allows fast writes for real-time topology and lightning speed traversals for real-time impact computations, which is second of all, the graph model is extremely flexible and agile. And integration and ingestions of data from multiple sources is extremely easy. And this makes it easy to accommodate changes in a very dynamic environment, which networks are. And a third reason is the standard services and API for integration with other solutions, and especially our declarative query language, Cypher. I'm going to hand over to Will, who will now give you a short demonstration on how to use graph model to show dependencies in an IT network. So over to you, Will.
Great, thanks, Alessandro. So as Alessandro said, what we're going to do here is model a very simple IT network, and we're going to look at a few different use cases and how we would use Cypher to query this network to answer some real-world questions. So first, let's look at the graph model of our network here. So we have a public website application that depends on a web server virtual machine and a database virtual machine. So pretty simple architecture for our public website. The web server VM runs on physical server 1. So here we're spanning layers from virtual machine layer to the hardware layer. And in turn, server 1 has a dependency on the SAN, the storage area network for disk. Now, our database virtual machine runs on physical server 2, which also has a dependency on the same storage area network for disk. And finally, we have a CRM application with dependency on the same database virtual machine that our public website is accessing. So very simple network here that we're representing as a graph. This can be modeled very easily in Neo4j. So let's see how we would use Cypher. So Cypher, the query language for graphs on Neo4j, to answer some real world questions. So the first question we want to answer deals with impact analysis, or a what if scenario. So what if server 1, so this server right here, what if this server goes down? What are all the services impacted by an outage in server 1? Well, to do that, we can just write a simple Cypher statement using a match. So if you haven't seen Cypher before, you can think of Cypher as SQL for graphs. Cypher is very much focused on pattern matching. So what we're going to do here is write a match statement, which is similar to a select in SQL, if you're familiar with that, and then specify the pattern, the graph pattern that we want to match on, and then we're going to return paths in the graph that match this pattern. So first we need to define the pattern that we're interested in. In this case, what we want to do is match on some service where the name of that service is server 1. So we want to start with this service here, server 1. And then we want to traverse out along these depends on relationships to find all of the dependent services of server 1. And now we can see that we have a direct dependence from the web server VM to server 1, but we're interested in the entire chain of services. So if server 1 goes down and the web server also goes down, because that depends on server 1, what are things upstream of the web server VM that are also impacted? So for this, we can use a variable length path operator on the relationship in Cypher. So we'll find all of the services that would be impacted by an outage of server 1. And the result we can see here colored in red would be the web server virtual machine and the public website. So if server 1 went down, both of these services would be impacted. Similarly, with dependency analysis, we want to know all of the services on which the public website depends to be operational. So again, we write a simple match statement and then the graph pattern that we want to match on in the graph. In this case, we want to start at the public website service and traverse out along the depends on relationship. And again, we'll use this variable length path operator to find all of the downstream services. And we can see colored in red here all of the services that the public website depends on to be operational, from the database virtual machine all the way down to the SAN for disk. And finally, we can do aggregates in our Cypher queries here. So if we wanted to know what is the most dependent upon component in our network, we can look at all paths in the graph and then do a group by here on the service, count the number of paths that we see that are connected to this service. And we can see here that the SAN which is our disk essentially is dependent on the most, has a direct or indirect dependency for every other service in the network. So that was just a simple walkthrough to give you an idea of how we can use Cypher and how we might model a simple network management graph in Neo4j. And so with that, I'm going to pass it back to Alessandro.
Thank you, Will. Okay, so let's move on and talk a little bit about the security graphs. And the nature of modeling network security data is actually very complex. And this is due to the fact that you often have to deal with storage of huge volumes of raw data. Also, the data in itself comes from different sources. It's constantly evolving, and it's often incomplete. And last but not least, you're dealing with a constant flow of newly generated data. And all this combined makes this a pretty complex task. So let's look at some of the challenges that the security operators face on a daily basis. The main purpose, of course, with a security operating center is to protect, detect, and investigate for security and loss prevention, right? And as with network management, this requires an ability to visualize an entire cyber posture, identify vulnerabilities, prevent attack, detect attacks, etc. And the key challenges here are, and the same with the network management, is we also see a wider range of fragmented security tools that are being used that don't really provide you with a visibility of context, which makes it difficult to predict intrusions and harder to model different cyber attack scenarios, right? And another way to put it is that companies today use a lot of different data security tools. You'll have one system for firewall rules, one system for intrusion detection, another system for security information and event management, etc. And leading almost to an overload in information, but without providing the necessary context. And this is a problem because without a clear view of your network topology, that will actually affect your ability to configure your cyber posture, your policy rules, etc., which will affect your ability to respond to cyber threats, identify incidents, and impact effectively. And this essentially affects your ability to take the appropriate action, set objectives, and form activities. So it's all a chain reaction that kind of begins with your inability to have a clear view of your entire network. And I'm going to show you an example of an attack graph analysis. And this is something that you can read more about in a blog post from the Neo4j blog. And this is an example of a way to analyze data in a way that prevents the cyber attacks. So it first takes an expression for how a network is segmented and how those segments fit together. Next, it examines the connectivity at a logical level and looks at known vulnerabilities across the endpoints of a network. And finally, it determines all the different ways in which an invasion could get routed through the network, including which firewalls it would pass and the rules applied to each of those firewalls. And each one of those source destinations could be a single movement in a potential multi-stepping stone attack moving through your environment. And one example of an attack graph analysis would be to map all these steps and expose bottlenecks and show how an attacker could navigate throughout the entire environment when you have sort of the whole system and all the steps stored in the graph. And I think this is an interesting quote, that in network security, it's often the little links between incidents that seem almost meaningless that are often what causes the largest problem. And that's why it's so important to have a unified cross-domain view of your networks and security measures. So let's look at an example of an architecture of how this could look. And this is also from that same blog post on the Neo4j blog. And in this example, you see how many different domains are ingested through a REST web interface and imported into a document database. Then all that data is captured and stored in the way that the data relates in Neo4j to be able to get the holistic, unified view of all the relationships and dependencies that you would want to analyze in the secure operating center. So these are actually like the screens that you want to be looking at. You want a holistic, unified view of your network topology and security measures. And that is why Neo4j is used in network security. And first of all, as with network management, in order to perform efficient security management, you need a complete visibility of your topology as it relates to your security rules, your firewalls, your vulnerability, etc. And you can't really achieve that without graph technology. And second, Neo4j provides real-time query capability, which is required when providing security over huge and highly interconnected networks. And we see Neo4j being used by telecommunication and cybersecurity firms for understanding network cyber posture, identify vulnerabilities, and trace network intrusions. We're going to show you, I'm going to hand over to Will again, who will give you a demonstration on how security graph works in Neo4j. So over to you again, Will.
Great, thanks, Alessandro. So what I want to do now is show how we might import some data, some network traffic data. So we're going to look at a public data set that's often used for malware detection, put out by the University of Victoria. This is network traffic data that we're going to model like this. So basically what we're going to be modeling is IP addresses that are connecting from some port to the ports on another IP address. We have information about the time that this connection occurred, the TCP flags, and so on. And we're going to see if we can uncover some possible suspicious activity based on the structure of this network. So again, this data set comes from the University of Victoria. I downloaded it, and it's basically a PCAP file, which was collected using Wireshark. So Wireshark monitors network traffic and is this binary file. So by itself, this is not extremely useful for us, but we can use the tshark command line program to pull out some fields here. So you can see we have a lot of information in the PCAP file about IP addresses, user agents, ports, and so on. So there's a lot of information that we can extract. I'm going to pull out just the subset that we're interested in and render this as a CSV file. So by running this tshark command and specifying the fields that we're interested in, we can generate a CSV file, which we can then import into Neo4j using Cypher. So this is the format of the CSV file that we generated from this data set that has our IP addresses, ports. We even have some geo information about countries and cities based on geo IP lookup. So just this subset of the PCAP file is a fairly rich data set. So let's jump over to Neo4j and see how we would import this data. So we're going to use load CSV to import this data. So if you haven't seen load CSV is sort of ETL tooling within Cypher to load data from a CSV file and then manipulate that using Cypher. So here we're loading the CSV file that we generated from the PCAP file. We're just going to look at the first 50,000 rows. And then we're filtering for rows that have IP addresses and ports. And then we're creating nodes here for the IP addresses and the ports that show up in the data set. Great, so we've created our nodes. Now we need to add some relationships. So again, we're going to iterate through this CSV file again. We're now going to match on the IP addresses that we just created, and now we're going to create these listening on relationships. So connecting the port, connecting the IP addresses to the ports that we know that these IP addresses are listening on, because we see connections in the traffic file. And so we've done that, and then finally we're going to create our connects to relationships. So this is where we've observed an actual connection from the port on one IP address connecting to the port on another IP address. And on this connects to relationship, we're just going to set some properties for some of the information that we have here, TCP flags, the frame, just so we can track that, essentially the line in our CSV file, and then the time that the connection occurred. So if we look back to the data model here that we're building out, this is what we're trying to model, is some connection from port, in this case 1036 on this IP address, connected to port 80 on this other IP address. So this is the graph that we've hopefully constructed here. It looks like this is complete now. So we can now query our graph to look at a subset of our graph here visually. So here are some IP addresses, just 25 at random. We can double click on these to expand out. So here we can see that IP address 6495.58.150 is listening on port 80, and it's had a lot of connections from port 1036 from this other IP address. And this is pretty typical behavior. So we have one machine connecting to the TCP for HTTP port 80. So it's pretty standard behavior there. So let's close that out. We can also query within the Neo4j browser for aggregate and tabular data. So one of the questions we might want to ask is, what IP address is accepting the most incoming connections? And so to do this, we just, again, specify the pattern that we want to match on, which in this case is some destination IP address that's listening on a port, and then looking for incoming connections to that port from the port on another IP address, and then returning the destination IP address along with this aggregate. So anytime we return an aggregate in Cypher, we get this implicit group by, and then we can order by that count. So we can see here that we've had 14,000 connections to 172.16.011. And similarly, if we wanted to see what IP addresses are sending the most outgoing connections, well, all we have to do is we can use the same pattern and just have to change the value that we have this implicit group by with. And we can see that the same IP address is actually generating the most traffic. And this is just a simple sample in a short window. So I think this makes sense, but it's not really clear to us if there's any strange activity going on here. So let's dig in and look at outgoing traffic for a specific IP address. So we can do this by specifying a specific IP address here, again using the same pattern, and now we can visualize this in the Neo4j browser. So here's the IP address 172.16.012. We see some outgoing connections to 6 other IP addresses, and these are all connecting to port 80 on these other IP addresses. And port 80 is the port most commonly used for HTTP traffic over TCP. So this is pretty standard pattern that we would expect to see in our traffic here. Now let's look at incoming traffic. So we saw a lot of requests to 172.16.011. So let's dig in here and take a closer look at what's going on there. So here's 172.16.011 that is accepting incoming connections from 4 different IP addresses. And what's interesting here is that all of these incoming connections are connecting from port 25 on these other IP addresses. Port 25 is the SMTP port, and there's a known vulnerability for botnet activity over SMTP. So this is potentially some suspicious activity that we have so many incoming connections on port 25, and we don't see these IP addresses generating other traffic. So one thing we can do to dig in a little bit closer here is look at what ports are all of the machines connecting to 172.16.011. What ports are they connecting from? And look at these in aggregate. So again, we're using the same pattern here for our IP address that we're interested in. Let's look at connections to all ports on this IP address, but then we want to look at what port these connections are coming from and order those by the number of connections. And when we do that, we see that the vast majority of the connections are coming from port 25 on these other IP addresses, 14,000 connections, in fact. So this is very indicative that we have some suspicious activity here from a botnet, and in fact, this is the denial of service attack that's going on from a botnet. One of our visualization partners did a good blog post on this to talk about using graph visualization with Neo4j on the same data set. So really encourage you to take a look at Lynn Curious's blog post on this to see how you can use graph visualization, again, with Neo4j on this data set for the security graph. Great, and so with that, I'll pass it back to Alessandro.
Thank you, Will. So that was a brief overview of how you could use graph databases and Neo4j to tackle problems related to network analysis and the security graphs. Just to sum up, we'd like to give you just a quick overview of who's using Neo4j and the adoption of graph databases. We have a wide adoption of this technology, from everything from government who uses it for its data operations to institutions like the World Economic Forum or ICIJ, and of course many commercial clients in the Fortune 100s like Walmart, eBay, LinkedIn, Cisco, etc. Neo4j is the most popular graph database around, so we have the privileged view on many use cases and usage of graph databases, and Neo4j is today used in verticals as diverse as software, financial services, retail, media, social networks, telecom, healthcare, etc. So, and all this across a wide range of use cases. So you can definitely say that graphs are really everywhere, and as we like to put it, we're moving towards a graph inevitability, and we see this in a lot of analytics report as well, and Gartner talks about graphs being the single most effective competitive differentiator for data-driven operations today, and they predict that by the end of 2018, 70% of all data organizations will have at least one or more pilot or proof of concept on their way. And Forrester goes so far as to say that 25% of enterprises will be using graph databases by next year even. So this is definitely something that we feel. We get a lot of tractions from basically all the industries to try out and use this technology to solve more connected related data problems. And I also want to give you a shout out for some valuable resources for those of you who want to learn more. If you're a developer, please visit our developers page. If you're interested in case studies and solutions, we have a lot of those. And there's a lot of interesting use cases and case studies at our solutions webpage. And if you want to learn more about the product in Neo4j, please visit our product page. And lastly, if you're in the Bay Area around October 13, don't forget to register for Graph Connect, which is our yearly event in San Francisco. There you can sign up for training, listen to customers sharing their graph projects, meet our Neo engineers and senior staff. It's a lot of fun, and I strongly recommend it if you're in town. So visit graphconnect.com for more information on that one. Thank you for participating in this webinar. Thank you, Will, for demonstrating a bit of Cypher and Neo4j for us. I hope this was useful, and reach out to us if you have any questions, and I hope to see you again soon.